Hey everybody, this is the second video for my Intro to Calculus students regarding their intro skill review worksheet that we're starting the course with. In the last video I showed some examples and a little bit of explanation of how to do 1 and 2. This will be a little longer video. This one's going to tackle all of the factoring skills, which encompasses 3, 4, 5, 6, 7, and 8. It also will tackle the factor theorem, which is something you do learn in grade 12, but it's not a big deal, as you'll see. It's actually a fairly easy concept. And actually we'll also get into something that we do need to do the factor theorem, and that is the ability to long divide polynomials. And that'll actually also help us do page 3 of this introductory booklet. So this video will take on everything from 3 to 8 and page 3 of this booklet. So this one will be a little longer. So buckle up and feel free to speed up the video if there's parts of this that you don't need to see. So anyway, let's start by reviewing some basic grade 10 factoring. So this is a ax squared plus bx plus c quadratic, where a is the value 1. So that's an easy one. Most of the time you kind of just guess and check this. You realize that to factor this, you need two numbers that multiply to make 12 but add to make -7. So if you're good with your number facts, first of all, if two numbers multiply to make a positive, either they're both positive or they're both negative. And if they add to make a negative, well, there's no way they could both be positive, so it's not that. So we know that we have x minus something and x minus something. So we've taken care of the signs. Now we just have to break 12 into two numbers that add up to make 7. And yeah, it's going to be 4 and 3. And if you can't do that, you might be in the wrong place. So that's number 3, or that's how you do number 3. Number 3 does have a few that get a little more complicated. Like if you looked at this and you'd probably go, oh no, that's different than this. A isn't 1. But remember, the first rule of factoring is that you always look for a common factor first. Now first of all, I'm going to rearrange this the way I normally would see a quadratic triplet or a trinomial. I would organize it in order of descending powers. And when I do that, it kind of should be clear that, oh yeah, there's a factor of -2 in all three of those. So always look for a common factor first, and then it becomes the same task that we had before. This -2 stays there, but now two numbers multiply to make -8, which of course if two numbers multiply to make a negative, they have to be opposites. And now what two numbers times to make -8 but add to make -7? Well, it's got to be -8 and +1. So there we go. So that's really all there is to number 3, just kind of grade 10 factoring revisited. For number 4, now a is definitely not 1, and there's no common factor trick I can use to make my life a little bit easier. So now what? Well, let's see. What I can do with this is I can use what's called factoring by decomposition. I'll keep my calculator handy here in case I need it. There won't be a single test this year where I ever take your calculator away, so even when the factoring gets tough, you'll be allowed a calculator if you need it. Basically, to factor by decomposition, you remember that, actually let me just get a piece of scrap paper here. When you factor by decomposition, you remember that if you were foiling, like let's say we had x plus 3 times, or let's put some coefficients on that. How about 2x plus 3 times 3x plus 5, for example. Remember that when you FOIL, you go first times first, so 6x squared, outside times outside, which is 10x, inside times inside, which is 9x, and last times last, which is 15. And I don't know if anybody ever pointed this out to you before, but if you've done this correctly, this coefficient times this constant, which is 6 times 15, which is 90, will be the exact same thing as this coefficient times this coefficient. Those two numbers make 90 when you times them together, and those two numbers make 90 when you times them together. And that's the way it'll always be. So decomposition is basically the idea that we're going to take this trinomial and decompose 7x into two numbers so that I can kind of factor the x's and then factor the constants. And the way I always approach this is, okay, well, I need two numbers that that add to make 7, but they multiply to make the same thing that 3 times negative 20 makes. So the first thing I'm going to do is figure out what 3 times negative 20 is, and it's negative 60. All right, so I need two numbers that multiply to make negative 60, but they add to make 7. So if they add to make a positive, then the bigger of the two numbers will be positive. So could it be 60 and negative 1? Well, no, those would add together to make positive 59, way too far apart. But if you don't feel like guessing and checking, you can do this kind of systematically. You can just list the factors until you hit the right pair. So that would be, let's see, that'd be 30 and negative 2. That's still 28, too far apart. 20 and negative 3. Getting warmer, those are 17 apart. I need 7 apart. 15 and 4, negative 4. Getting very warm, that's 11 apart, but I need 7, not 11. So it's the next pair. It's 12 and negative 5. If you add 12 to negative 5, you get 7. So I'm going to then say plus 12x minus 5x. And this is why it's called decomposition. We basically decompose 7x into 12x minus 5x. And the reason we did that is because now we can factor out a common factor in both these terms. So I'll factor out 3x in these two terms, leaving me x plus 4. And then I'm going to factor out negative 5 from these two terms, which leaves me the same bracket here that it does here. Now I think of this like it's 3xy minus 5y, and I just factor out the y. Just in this case, the y happens to be a whole binomial instead of just a single factor. Still a single factor. But there we have it. That's factoring by decomposition. That's the biggest, baddest thing you do in grade 10 factoring. So practice that from number 4. That will pop up a couple times. Then in number 5, it is factoring a difference of squares. This is pretty easy to just memorize, that if you have a perfect square minus a perfect square, you take the square root of the first thing and the square root of the second thing, and then one's a plus and one's a minus. And if you're wondering why that works, you can say that in general, if you have any x squared minus y squared, so in this case x could represent this whole thing, or actually I don't even have to use x and y if it confuses you. Here we go, a squared minus b squared. A can represent 16x squared, a can represent 4x and b can represent 9. If you take any one of those, it's always the square root of this one plus and the square root of that one minus. And there's a very good reason for that. If you FOIL that out, remember that you're going to get a squared plus ab minus ab minus b squared, and those two terms will always cancel. So another way to think about it is, you are if you start with a squared minus b squared, you could think of it as a squared plus 0 ab's minus b squared, and then you're just asking yourself what two numbers times to make 1 but add to make 0, so it's obviously plus 1 and minus 1. So there we go. That's the way this one works. This, by the way, these are called conjugate pairs, and I always like the little rhyme that a difference of squares makes conjugate pairs. Conjugate means that they're the same terms, but one is the pair of terms are being added, and the other one, the pair of terms, is being subtracted. Don't call them opposite terms. They're not really opposite. The opposite of 4x plus 9 would be negative 4x minus 9. So they are called conjugates, difference of squares and conjugate pairs. If you're good at remembering that little rhyme, you'll never forget how to do it. Number 6 asks us for factoring differences and sums of cubes. And that is something that not every grade 11 teacher gets to. If you were in the honors program, you've seen it for sure. At least I would do with my honors kids. Let's start with in general. In general, a cubed plus b cubed will always be I'm going to cover that up for now. A plus b, because you just cube root that, keep the sign the same. And then it'd be a squared minus ab plus b squared. If you don't believe that this thing multiplies out to become that, feel free to multiply it out. In fact, we'll do it. It only takes a sec. A times all of this would be a cubed minus a squared b plus ab squared. And then b times all of this, I'm going to rearrange the order, but it's a squared times b, so that'd be plus a squared b, and then b times this would be minus ab squared, and then b times b squared is going to be b cubed. And look at all the terms that cancel. You have minus a squared b plus a squared b. You have plus ab squared. You have minus ab squared. I'm getting some real shadows here. Maybe does that help? Maybe a little. Best I can do. Anyway, notice that you get this. So there we go. This is the general form of the way a sum of cubes, this is what you call that, just like the last one was a difference of squares, this is called a sum of cubes. But what's neat about cubes is that it can be a sum or a difference. Back when you were doing difference of squares, it has to be a difference. There is no way to factor a sum of squares. But with cubes, you can factor a sum of cubes, or you can factor a difference of cubes. If you have a cubed minus b cubed, you will say that the general form of that is a minus b times a plus, notice the sign is different, sorry, a squared, plus ab and then plus b squared. There we go. Sorry, lost my train of thought there for a sec. Got distracted. There we go. And that is always the way it's going to look. How do you remember to get this, and how do you remember to get that? Well, I actually, just like I remember for difference of squares, I remember a little saying, a little rhyme, conjugate pairs, difference of squares. For my sum and difference of cubes, there's a haiku. First, square the first term, then the opposite product, then square the last term. That's a haiku because it's 575. Remember that from poetry class? If you're having PTSD because I'm making you remember poetry class, just how about square the first, change the sign, times them together, and then square the last. So anyway, they all work like that. Let's just do one as an example. Okay, so cube root the 2 for the bracket here. It's 2x minus 5, right? That's the perfect cube of that, perfect cube of that. And then square the first, change the sign, times the two together, and square the last. And there we go. Then you look at this and go, can I factor that one? And I'll leave that one to you. Does that one factor? Let's see. Well, it looks like it might. 2 times 5 is 10. Oh, but that would have to be 20 if that factored. No, actually that does not factor. Ha! There, I didn't leave it for you. I just told you anyway. So that was number 6. I'm going to jump to number 8 now. I'll come back to 7 in a minute. Number 8 is stuff you did in grade 11, and it's more factoring. It says simplify and state, I call them NPVs with my grade 11s. It's non-permissible values. So if I want to simplify this, I'm going to do some factoring. So let's see. If I factor the top of this thing, let's see. Once again, I'll use my decomposition method. 2 15s is 30. And I have two numbers that have to times to make 30. They add to make a negative 13, so clearly they have to both be negative. And the two numbers that times to make 30 that would add to make 13 are negative 3 and negative 10. So I have 2x squared minus 3x minus 10x plus 15. On the bottom, let's see, 2 and negative 3 make negative 6, and two numbers have to times to make negative 6 and add to make negative 1. So they are clearly negative 3 and positive 2. I said positive 2. So that's going to be 2x squared minus 3x plus 2x minus 3. All right, on the top, I can factor out of here an x, leaving me 2x minus 3. And I can factor out of here a negative 5, leaving me 2x minus 3. On the bottom, I can factor out of here an x, and I would be left with x minus 3. And on the bottom, I can't really factor out anything, so I'm going to factor out a 1, leaving me 2. Oh, whoops. Should be a 2 there, I'm sorry. Leaving me 2x minus 3. So on the top, 2x minus 3 is a common factor of those two things, so I'm going to factor it out. 2x minus 3 times x minus 5. And on the bottom, 2x minus 3 is a common factor, leaving me x plus 1. And now that I'm completely factored, I can say that those two things divide and make 1, i.e. they cancel. So the final answer here is x minus 5 over x plus 1. Now, hold it, I'm not quite done. I wanted non-permissible values, and there are actually non-permissible values here. Now remember that you can't ever divide by 0. So if I have a number times a number on the top, well, I don't really care. Those can be 0. But on the bottom, this number times this number can't be 0, and that number can't be 0. So my NPVs are that x equals -1 is not permissible, because then I'd have -1 plus 1, and I'd be dividing by 0. And then 2x minus 3 can't be 0, so x equals 3/2. And if you're wondering how I got that, think about this. 2x minus 3 can't be 0, so 2x can't be 3, so x can't be 3/2. Okay, so that's the solution. Basically what this is saying is, see this big ugly chunk of algebra here? It can be simplified to that much prettier piece of algebra, a much more efficient piece of algebra here, if you avoid -1 and 3/2 for x. In other words, for every number in the universe, that is the same expression as that, except for those two numbers. So that's what you're doing, and you learned how to do this in grade 11, but here in grade 12, and here in the intro calc, sometimes the things are a little uglier than the things you had to factor in grade 11. I'd just like to point out that the most common mistake people make with this is they forget what they're doing, and then they'll just look at this and go, oh, I get to cancel stuff. And they cancel those two things because they think, well, I can cancel them. It's the same thing on the top and the bottom. And that is quite wrong. I'm going to erase that. That hurt that physically hurt me to do that, because that's not how you cancel. First of all, canceling isn't actually a thing in math. It's a shortcut word that we use. There's two things we use when we say cancel. We say that when we add opposites, we cancel them. And we say that when we divide something by itself, we cancel them. Really, at the end of the day, we just made it a 1. This divided by this is not going to help here. Whenever I see somebody make that mistake, I always ask them to do this. I always say, okay, here, can I point out something to you? I say, suppose I had 2 plus 3 over 2 plus 5. So that is 5/7, right? Well, can I cancel the 2's and say that it's 3/5? Does 3/5 equal 5/7? And then there's people who go, oh no, but you can cancel it and make them 1's. Fine. Does 1 plus 3, does 4 over 6 equal 3/5 or equal 5/7? No, none of those fractions are the same thing. You can't cancel that way. The way to remember it is, you can cancel, and by cancel again I mean divide something by itself, when you are completely factored. You can cancel factors, you can't cancel terms. So keep that in mind, and you'll never, if you remember that rule, you'll never make that god-awful mistake. So that's number 8. Now I'm going to kind of jump back to number 7, which is the factor theorem. And the factor theorem states, and this sounds real formal, but it's actually a pretty simple idea. It states that if the function of some n value is 0, then x minus n is a factor of f of x. Now that doesn't sound all that thrilling until you see how useful it is. Now when I look at this thing, is it a trinomial I can factor? No. Is it a sum of cubes or something? No. I don't have any tools in my toolbox to factor this with the tools that we've just been using. So what I do is I set this to be f of x. And then I try to find values that I can substitute in for x that make this thing 0. So the first one I'm going to try is, well, I'm going to try maybe 1. Let's try what happens when x is 1. What's f of 1? Well, f of 1 would be 1 cubed minus 6 times 1 squared plus 11 times 1 minus 6. And lo and behold, it's like I knew this was going to happen or something. This is 1 minus 6 plus 11 minus 6. And that would be, oh, hang on a sec, something's gone wrong here. Hang on. Did I copy this wrong? Let me double check. Let's see, 5x squared. Did I do this? Did I copy this wrong? X cubed minus 6x squared plus 11x minus 6. That's 1 minus 6 plus 11 minus 6. Oh, no, I didn't. Oh, look at that. I'm just doing the math mentally wrong in my head. You're all probably watching the video going, no, that's 0. You're right. 1 minus 6 is -5. -5 plus 11 is 6. 6 minus 6 is 0. Duh. Sorry. It's getting late. I'm having a brain cramp. That is 0. So f of 1 is 0. And the factor theorem tells us then that that means that 1 is a number that makes this expression 0. Therefore, x minus 1 has to be a factor of this. Now, here's where I'm going to kind of pause. X minus 1 is a factor of this, but how do I figure out the other factors? Well, think about it this way. If I gave you a number like, I don't know, 216, and I told you, hey, guess what? I know 6 is a factor of that. What's one of the other factors? What would you do? Well, you'd go, oh, no problem. I'll divide by 6. 6 goes into 21. Let's see, what does 6 go into 21? 6 goes into 21. 3, carry the 3, and 6 goes in. Oh, it's 36. So it's 6 times 36. So in other words, when I know a factor of a number and I want to know other factors, I have to divide by the one I know. So that's where we get the need to divide using algebra. I need to be able to divide this polynomial by that binomial. And that's not something you learn how to do until grade 12. So let's actually get into that. First, let's do a quick refresher on just long division in general. Again, some of you haven't done long division in a while. First of all, let's just talk about division. What is division? Well, division is repeatedly minusing a number, right? If I keep minusing 3's from 75, how many will it take till I run out? So, I don't know. Think about it this way. Is it maybe easier to think of it as a divide this way? Is it easier to think in terms of long division like this? They all give you the same answer. You might look at this one even and go, well, hey, you know what? I know 3 I can factor out of 75. Oops. 3 25s is 75. Then I'll cancel the 3's, and the answer is 25. So that works. I might do it as long division. How many 3's go into 7? 2 of them. 2 3's is 6. Bring down the 5. 3 goes into 15 5 times, and 5 3's is 15. If long division isn't something you remember doing very much, it'd be a good idea to kind of brush up on it. If there's people here who went through grade 12 and went, oh, my teacher never made me use long division. We did it by synthetic division. You can use synthetic division if you want, but I'm going to save that for your grade 12 course. And in this course, I think we'll stick to the long division when we need it. So that's long division with numbers. Let's do it with uglier numbers. Suppose I wanted how many, or what is 49,700, or sorry, let me say that again. 4,978 divided by 21. Now, one thing I didn't bother to do with this, going back for a second, is remember that I can also write 75 thirds as, if I wanted to, I could write it as I can simplify it down to 25 over 1, right? That one simplifies very, very nicely. This one doesn't simplify. So what I can do with this is, here, you know what, maybe before I go any further, let's stick to the easy one. Suppose again I had 75 over, but instead I had 4. Now, 4 for sure doesn't go into that number, but it does go into 72 and 76. In fact, I could say, if you like, that it's, let's see, 4 goes into 7 once with a 3 left over, so it's 18 3/4, right? Remember that? So mathematics tends to like this as a better answer than that. I know that in elementary and stuff, it's like, oh, early junior high, it's like, no, we want a mixed number. When you're dealing with algebra and stuff, actually improper fractions are definitely the way to go. But those two things say the same thing. It'd say the same thing if it was 18.75 as well. And remember, I could get that in long division as long as I just keep going. 4 goes into 7 once. Bring down the 5. 4 goes into 32. 8 times 8 4s is 32. And then do you remember what you do with that? You can say 5 minus 4 is 3. And then if you wanted to, back in elementary, you'd have even said you'd have just gone remainder 3. Right? Remember that? But we're not going to let you get away with that here in high school. That's baby talk. We're going to say either we keep going and make a decimal out of it, or since decimals are kind of passé, why don't we just make a fraction out of it? It's an easy decimal to make. You just go, okay, bring down a 0, and remember that there's a decimal place there now. And 4 goes into 30 7 times with a remainder of 2. Bring down another 0, and 5 finishes that off. But if you wanted to, you didn't have to do this. You could have just said, well, my remainder was 3, and I expressed the remainder over the denominator. So it's 18 3/4. And doesn't that make sense? Isn't 3/4 0.75? So with that in mind, let's do a big number one now. No decimals, no elementary remainder where we just write r in the remainder part. We want to express it as a fraction when we're done. So how many 21s go into 49? So let's count by 21s. 21, 42, that'll do it. So 2. So subtract, bring down. 21, 42, 63. The next one's too big. So 3 21s is 63. 7 minus 3 is 4. 7 minus 6 is 1. Bring down an 8. 21 into 148, I think that's going to go in 7 times. 7 21s is 147. There's a remainder of 1. And again, I could put a decimal down and keep going. You actually want to see what it would be? Let's see. What is 1/21st as a decimal? Oh yeah, this calculator doesn't like decimals either. Blah! Takes 6 digits for that to repeat. That takes too long. I'm going to just say that this is the remainder over the denominator, so it's actually 237 and 1/21st. And think about that, if you like, as plus 1/21. And that's the way we're going to approach the algebra. So, first of all, this is the way this is in page 3, by the way. So I'm going to do this page 3 example. Or actually, no, I'm changed my mind. I'm going to do this example here, this example from number 7. So I'm supposed to factor that. Oh, actually, wait a minute. Why am I doing that? I have an example I didn't finish, right? Where did I put it? Number 7, where are you? There you are. No, that's not you. Okay, I don't remember where I set it down. I have missed. Oh, there it is. Ha, there. So back to the example we didn't finish. So I want to factor this thing, and I know that's a factor. How do I find another one? So I'm going to factor here. I'll write it on the next piece of paper. I'm going to factor by dividing. How many x minus 1s go into, and what was it again? X cubed minus 6x squared plus 11x minus 6. There. So let's long divide. Okay, now let's put the other long divide that I just did. What was it? There it is. Let's put it beside it so that we can see what the steps are. Okay. So what was my first step? How did I get this 2? Oh yeah, I went, how many 21s go into 49? So how many x's go into x cubed? What do you times x by to get to x cubed? Well, you times it by x squared. And then x squared times x is x cubed. But don't forget, this is one number to me, so if I'm timesing this thing by x squared, I have to times that thing by x squared, and negative 1 times x squared is negative x squared. Now, how did I get this 7? By subtracting this from this. So I'm going to subtract. I'm going to do it with a bracket so that I don't goof up the negatives. So negative 6x squared minus negative 1x squared is negative 5x squared. Now, how did I get this 77? Because this 7 came down. This 11x comes down. And then I repeat the process. How many 21s went into 77? Well, how many x minus 1s go into negative 5x squared plus 11x? X goes into negative 5x squared, negative 5x times. Whoa. Negative 5x times x minus 1 is negative 5x squared plus 5x. I'm subtracting that. Negative 5x squared minus negative 5x squared is nothing, which is what I wanted. 11x minus 5x is 6x. Bring down the last. And how many x's go into 6x? 6 of them. 6 times x minus 1 is 6x minus 6. And no remainder means that it goes in evenly, right? Or no number here means there's no remainder. It goes in evenly. So x cubed minus 6x squared plus 11x minus 6 is equal to, remember the first factor we had was x minus 1 times that, x squared minus 5x plus 6. And I think I can factor it some more. Doesn't that factor? What two numbers times to make 6 and add to make negative 5? That's right. X minus 2, x minus 3. There. We have completely factored that big 4-term polynomial with an x cubed in it. And we use the factor theorem and long dividing. Let's do one more. If that's enough, feel free to turn off the video and go do something else. Or go try your homework yourself. So this is kind of like this is like number 7. So, factoring. Okay, there's actually one other thing about the factor theorem. There's also something called the remainder theorem, which says that when I tried, the first number I tried last time was what if x is 0? Well, I don't think x is 0 is going to work this time. Or sorry, I tried x is 1. X is 1 isn't going to work this time. It's not going to give me a 0. So I'm going to try 2. And then I'm going to try negative 1. Then I'm going to try negative 2. And then I'm going to stop. Why am I stopping? Because there's something called the remainder theorem that says that if this thing is factorable, the whole number factors, or the integer factors, have to be factors of 2. So that means it has to be plus or minus 1 or plus or minus 2. So I'll try 1. Does 1 work? What's f of 1 through here? I'm pretty sure it doesn't work. It's going to be 1 minus 3 minus 9 plus 2. Yeah, that's not going to be 0. So no, it's not 1. Is it negative 1? Let's see. We'll try negative 1. So that'd be negative 1 minus 3 plus 9 plus 2. Closer. That's negative 4 plus 9 plus 2, but that's still not 0. So then I'm going to try 2. Let's try 2. 2 makes this 8 minus, hang on, 2 is 4, and minus 12 minus 18, and I can already tell that that's not 0. That's way more negatives than I have positives. So the last one, I'm going to try negative 2. So negative 2 makes this negative 8. That's still minus 12. But now that's going to be plus 18 plus 2. And look at that. Negative 20 plus 20. That works. Therefore, x plus 2 is a factor. And then I'm going to long divide. So let's do our long divide together. Cover that up for now. So x plus 2 has to go into x cubed minus 3x squared minus 9x plus 2. Okay, how many x's go into x cubed? X squared of them. X squared times 2 is 2x squared. Don't forget you're subtracting. Negative 3x squareds minus 2x squareds is negative 5x squareds. Bring down minus 9x. How many x's go into negative 5x squared? Negative 5x of them. Negative 5x times x is negative 5x squared. Negative 5 times 2 is negative 10x. Negative 5x squared minus negative 5x squared is nothing. Negative 9x minus negative 10x is 1x. Bring down the plus 2. And then that's going to be plus 1. 1 times x plus 2 is x plus 2. And no remainder. And therefore my answer is x plus 2 times x squared plus 5x plus 1. That is the factored form of this. And in this case, can that factor? No, there's no numbers in the universe where 2 of them multiply together to make 1 and add to make 5. At least nowhere, not in real whole numbers. So that's it. Factored. All right, so that's how you do number 7. You use the factor theorem, find a 0, make a factor from that 0, and long divide. The page 3 is just about long dividing, and I've picked one that's a little bit trickier. It's got a trick to it. Notice that there's no x squared term. When I long divide, I need a placeholder for that x squared term. So I write down x cubed, and then I write down plus 0 x squareds. If I don't do that, my long division doesn't balance out and work out properly. The algorithm for long division is very finicky. There has to be something in each place. So minus x minus 1. So there's x cubed, there's minus x, there's minus 1, and because there's no x squared term, but I need one to make this work out, I put plus 0 x squared. Okay, this one also is going to be different than the other ones in that this one will have a remainder. So let's see what happens. How many x's make x cubed? X squared of them. X squared times x is x cubed. X squared times 4 is 4x squared. I'm minusing that. 0 minus 4x squared is negative 4x squared. Bring down minus x. X times what is negative 4x squared? So it'd be minus 4x. Minus 4x times x is negative 4x squared. Minus 4x times 4 is minus 16x. I'm subtracting. Negative 1 minus negative 16 is 15. Bring down a 1. And x goes into 15x 15 times. So that's 15x. 15 times 4 is, what is 15 times 4? 60. So my remainder is negative 1 minus 60, which is minus 61. So I would write my remainder as a fraction there. So that's going to be, my final answer is going to be that this divide is equal to x squared minus, oh, I'm off the page, I'm sorry, x squared minus 4x plus 15 minus 61 over x plus 4. Okay, and did I goof that up? 0 minus 4x squared minus x, and 4x times 4. Yep, no, I think that's right. There we go. Okay, cool. That should take you, or should allow you, if you can follow those examples, to do everything on this sheet except 9 and 10. I'll do those in a separate video. And you can now try page 3 with all the long division on it. Okay, and that's it. Thanks for watching, everybody.